All right, so let's go over quick sort since that's what we went over last in class. We all have it fresh in our minds. Okay, so we talked about a couple of ways of selecting the pivot element. And one way was to look at the left, right, and center elements and take the median value. And so this will give us a good indication of what the middle value of all the elements are so that we can try and split our list evenly into two lists. Okay, so what is the median of these three values? 61 lies in the middle of 13, 61, 95, right? So we want to pick that as our pivot, and then what we're going to do is swap it into the lowest position, and then we have these markers low and high. And what we're going to do with low and high is low is going to move to the right until it finds a value greater than the pivot, and then high is going to move to the left until it finds a value less than the pivot. So where is low going to move to? 91. Okay, and where is high going to move to? It is already less than the pivot, so it's going to stay. And then at that point, we're going to swap those two elements. So we're swapping 91 and 13. So we swap those two elements, and then we just keep doing that. So if we go and look at the code for quicksort partition, so while low is less than high, we're going to continue moving low to the right, so increase low, while low is less than high and the value at low is less than the pivot, right? So we're looking for a value greater than, then we'll stop. And same with high, but opposite. So we want to move high to the left while we find a value that is less than the pivot, and then we stop. At that point, if low is less than high, we swap the value at low and high. If low is not less than high, we exit and we swap the pivot with the value at high index. So let's continue doing that till we get to the end here. So where will low go next? 73. And then where will high go next? 24. So then we'll swap those two values and keep doing this. So where will low go next? And then high will go here. We swap those two. And now where does low go? 62. Now where does high go? 28. So at this point, low and high have passed each other. So what we do is we get to that stopping condition for our loop, and we get to the last step, which is to swap the pivot with high. So we're going to swap 61 with 28. So now what we notice is everything to the left of the pivot is less than, everything to the right of the pivot is greater than. So now we have fixed that pivot. So basically for quicksort, the reason why quicksort is fast is because we do all the swapping in place in the same array. But what I'm showing down here is what values are fixed. So now the only value that's fixed is our pivot, and we still now have to recursively sort the left side and the right side. So let's go do that. First, let's look at the code. So, okay. The code for quicksort is pretty simple because all the work is done in partition. Basically, we get our split, which in this case would be the index of 61, and then we recursively quicksort the left side, which is low to split -1, and the right side, which is split +1 to high. So we do the left first. So let's go do the left. Okay, so now again we need to pick our pivot between the left, right, and center. What is the median? The right, yes. So we will swap that into the low position, and now we have the pivot here, and then we move low until we find a value greater than. So where is low going to be? And where is high going to be? Right. So now they've already passed each other, so we just swap the pivot with high. And now that list is done. It's partitioned. So now we notice that 24 is fixed. We're never going to look at it again. But we have to recursively quick sort the left side and the right side. So we do the left side first. Oops. And basically, we would have left, center, and right. So the value on the left is always going to be the median. So we'll pick that as the pivot because we're at like a weird base case where we only have 2 elements. And again, low and high are on top of each other because we're on the base case. So basically, we move low till we find something higher, move high till we find something lower, and we don't have to swap anything because it's already sorted. So what we notice is that 13 is fixed after that partition. And so all we have to do is quick sort the right side of that array. So quick sorting one element is just basically returning that element. So now that value is fixed. So now we've done the whole left side of this array. Now we need to do the right side, which is just a single element again. So we don't really need to do much work. Now that value is fixed. So now we've completed the quick sort of the whole left side of the array. So if we look at these values which are completed, this is a sorted list, right? So now we need to do the right side. So we call quicksort from where the pivot is +1 to high. And now again we pick the pivot element from the left, right, and center. So what value is that going to be? All right, so we swap 91 into the first position. So we swap it with 62. Oops, that didn't work. Okay, so now low moves until we find something higher. So where does low go? All right, and then high is already lower, so we just swap those two. And then we move low into where? And then high to where? Okay, so now they've passed each other, we swap the pivot into high. So now we notice, okay, that should go away. Ignore that. Okay, so now that we notice 91 is fixed and the left side is less than, the right side is greater than. So now we just keep doing this process. I'll just keep doing it so that we can finish the whole sort. Okay, so what's the median now? 73, so we don't need to swap it anywhere where it's already in its correct position. Whoops. What am I doing? There we go. Okay. So now we move low till it's higher, high till it's lower, so those stay, and we swap low and high. Okay, and so now again, we move low till it's higher, that would be here. High till it's lower, that would be here. And now we swap pivot and high. So now that list is partitioned correctly and 73 stays. So now we just have to recursively do the left, which is a single element. So that is really no work at all, single element. And then we just have one more element left because we've done all of the left of this. Now we just have to do the right of that list. And so now the list should be sorted. Okay? Yes?
What are the conditions for selecting the pivot?
So you can select the pivot any way you want to. In the function that I showed before, we just randomly selected it. But for this, we're using the median of 3 method. So this is called the median of 3 method for selecting the pivot. And what you do is, let's say, we have an array of size 10 that goes from index 0 to 9. And we call partition. Can you not talk while I'm talking? Everybody okay? I just don't want to scream over everybody. Okay. We have low to high. So we call partition on this array. All right, now to get the pivot and index, what we're going to do is we're going to have, so we have low here, high here. We have to find the center. Is equal to low plus high minus low. I'm just abbreviating over 2. So if we do high minus low over 2, what do we get here? 9 minus 0 over 2 is 4.5. If it's an in, it rounds down. So we get here is the center at index 4. So what we do is we just look up what values are in each of those positions and get the middle one. That is going to be our choice of pivot. And why might we want to choose the pivot in this way? Why? Let's say the list was already sorted. Would that be a good choice of pivot? Why? So, let's say this list is already sorted. We would choose the median of low, center, and high, which would be 10. And then when we partition this list into 2 sides, it's going to partition evenly, and that's going to give us the best case runtime of quicksort, which is big O of n log n. Okay? So any other questions about that? Not always using the pivot in the middle. I guess it's just a way of kind of randomizing it and just selecting 3 numbers and selecting the median. Statistically, that's the best way to do it instead of always picking from the same spot. Yeah, I don't really have a good proof for that, but that's statistically what's the best method for a quicksort. Okay, so we've gone over quicksort, and what I wanted to show for the runtime is this. Okay. All right, so best case, we come up with this recurrence relation where we evenly divide the array into half each time, and then recursively call quicksort on each half. And then we also have the runtime for partitioning the list. And so what I solved in class is if we use the iteration method and solve this, we get that this is big O of n log n. So that's why in the best case, the runtime of quicksort is n log n, because we're always evenly dividing the list. Okay, so let's look at the worst case runtime of quicksort. Okay, so this is bad quicksort. Let's say that instead of picking the median of left, right, and center, we're always going to pick the first element. And this list is already sorted. So we pick 2 for our pivot, and we move low until it's higher. Well, low stays, and then we move high until it's lower than the pivot. So where does high move to? 2, yeah, exactly. So it looks at every element in the list until it gets to the pivot. High and pivot swap, so really nothing happens. And what ends up happening is pivot stays where it is. We recursively sort the left half with it, which is nothing, and recursively sort the right half, which is n minus 1 elements. Okay, and then again, we're going to pick the leftmost element as our pivot, and the same thing is going to happen. We're going to search through the whole list through n minus 1 elements, and then we're going to recursively sort n minus 2 elements. And the same thing's going to happen. So we're just reducing the list by 1 each time. Okay? So then there would be a couple ways of showing the runtime for this. So, so we can show the runtime and write as something like this. So we recursively sort n minus 1 elements each time, and we could solve that and show its order n squared. Or we notice that each time we do a step, we end up doing 1 plus 2 plus 3 plus n minus 1. And so we know that that summation comes to be what? Does anybody remember the formula? N times n. Well, actually, so if we plug in n minus 1 into the formula, yeah, so it's n minus 1 times n over 2. And then if we multiply that out, we get n squared minus n over 2, which is big O of n squared. So that's why the worst case runtime of quicksort is n squared. Okay, any questions so far? All right. So last thing I want to show is merge sort. Okay, so basically what merge sort does, if we look at the code for that, is it divides the list into 2 halves, recursively merge sorts the first half, then the second half, then merges the results of those 2 values, of those 2 resulting lists. Okay, so let's look at that. So we do the left half first, then we merge sort the left half, and then the left half until we get to the base case. At this point, we can merge those 2 values up. So what we do, if we look at the merge function, is we have 2 counters starting at the front of each list. So basically, oops, we pass in one list that's values that starts at start to middle is the left half, middle to end is the right half, and we start a counter at count 1 at start and count 2 at middle. So we're trying to merge those 2 subarrays from start to middle and middle to end. So if the value at count 1 is less than the value at count 2, we copy the value at count 1 into our merged array. So what we're doing is we're keeping track of this temporary array. And if the value at count 2 is less than the value at count 1, we copy that value over. And so what we end up with is the merged values in this temp array. And so the reason that quicksort is faster in practice is it doesn't copy things over. So this is always copying into a temp array. So quicksort does everything in place so that it doesn't have to copy things over, so it's faster in practice. Okay, so what we're going to do is compare what's at count 1 to count 2 and which one would we take and copy over. we would take count 2 because it's less, then we would take 76 because it's left over. So now this is merged, and is that list sorted? Yeah, so merge is what is actually doing the sorting for us. So now we have successfully merge sorted this left half. Now we need to do the right half. Okay, so we do the right half of that one. And then we do the left half of that and the right half. So this single element is complete. Now we just have to finish the right half. So we go down to the base cases, one single element, and at that point we merge those values up. Well, that's already sorted, so we don't have to do much work there. Oops. Yeah, so what we're doing to divide it in half, we're doing end minus start over 2 to get the midpoint. Does that make sense? 2 minus 0 over 2 is 1 is the midpoint. And so I guess, yeah, we do from start to mid minus 1 is this side. Then we do mid to end. Okay, so now we need to merge these values up. So we compare the value at count 1 to count 2, and which one do we merge up first? Copy it into our array. Count 2. And then we compare count 1 to count 2. Which one do we take? Count 2. And then we take count 1. And now we have done, so we originally did the merge into here. Then we did the merge into here. And then we did the merge into here. So we did 1, 2, 3 merges. Now we're about to do 4. Okay? So which value do we take? Count 2, then count 1, then count 1, count 2. Whoops. Am I doing that wrong? Yes. Okay, count 1 is less. And then count 2, then count 2. Okay, so that's successfully merged. So what we have done is now sorted 5 values with 4 merges. We did 1, 2, 3, and 4. Okay? And so now we need to do the right half of this array. Okay, so again, we just keep calling merge sort recursively until we get to the base cases, and that's when we start merging up. So we take count 1 and then count 2, then we do the right side, and we break it down into the base case. We do the left side. Oops. And then the right side, left side, right side. Okay. So now we merge count 2 up, then count 1. Now, which do we take? Count 2, count 1, count 2. And so what we've done so far is we did the 4th merge, and then the 5th merge, the 6th merge, and now we're about to do, wait, hold on. 1, 2, 3, 4, 5, 6, 7. Okay, and then we're going to do the 8th merge right now. And so we notice that the merge function is order n because we start the counts here, and then they just look at each value, so one time. So if it just looks at each value one time, it's order n. Okay, so then we take 2, 1, 2, 2. Okay, so now we are done with the left and right side. So the very last step is to merge everything into one sorted list. So we take count 2, and we just keep comparing and taking the lesser one. And then count 2, count 1, and then count 1, oops, and then count 2, count 1, count 1, count 1, and then we're done. Okay, so hopefully that gives you an idea of how merge sort works and the merge function works. Okay, so what is the runtime of merge sort? Anybody remember? It's n log n, because if we go back to, let's see if I can, right there, no. Okay. Because we're evenly dividing the list in half every time, no matter what, we're calling merge sort on half of the list 2 times, the left side and the right side, plus order n for the merge. So if we solve this like we did in class, we get big O of n log n. And so if you want to think about it this way, we have the n for the merges, the log n for dividing the list in half each time. And so really the best case, worst case, whatever case of merge sort is the same. It's n log n. Okay? So any questions about that? Nope. Okay, I guess we're going to have a quiz then. Yeah, surprise.